So it's really a pleasure to be back here in Big Data Spain and see that all the growth that is happening. The talk has a title as Managing Data Science, and it was an intention of giving you some tricks that data scientists may know from theory on how to manage the process of making a project successful. But it can also be interpreted from the point of view of education about big data that we need in the industry. So in one of Amparo's slides, you can spot one number that maybe got unnoticed, that it says 1.5 million managers should be educated in data science and machine learning. And I could try to show why and try to shed some light on what should we educate people on. So I work as a data scientist. I chose this field of knowledge like 10 years ago, and the main reason that I chose it is because I wanted to use my knowledge on computing and apply it on very different problems and really understand more other areas of knowledge than the computing in itself. And it has been great. I cannot think about any other profession that I could have chosen. And I have gone to many different places and I have applied my knowledge in very different areas of expertise. But for some reason, I have always fell in a place where data science was new. And let me share with you, sometimes it's really frustrating. And why is it frustrating? Well, I've been in many data science first meetings when a company says, okay, we want to do data science, we want to do a new project. And it usually feels something like that. It feels like people don't understand each other, they don't really know what they are looking for, and when you're actually trying to guide them, they actually don't understand what do you mean. So it's like people have different mental models about what this data science is. I have experienced some weird moments, and I have learned with time to detect when something is going to go wrong. So I want to share some examples just for you to have this very same experience. So I've been in places, for example, where they say, I prefer not to give you any insight of the problem, and they actually would ask me, why do you know where the data comes from? For you, you are a data scientist. For you, this is just columns and labels. I've been in another project, and the case there, well, yeah, we actually had the data. They actually explained the problem to us, but they actually told us, do not have any reference labels. I mean, they exist, but why should I share that with you? You just tell me if the problem, if you can do something with it, and if it makes sense. There was another weird moment where we were trying to do some predictive maintenance on windmills, and vibration signals are very messy. It's a kind of very messy signal, and actually the idea of the person was, why don't you just take a screenshot and feed that into the algorithm? I've been told that image processing is actually working very well. Not really good advice. And there is also the last one is actually very usual. It's like when you give the result and the feedback you get is you're wrong. How can you be sure about that? I've been doing this business for a long time, and that you cannot be right. Why do you have to show me that you have some guarantee that the result actually is true? But that's not always the case. I'm also 50% of my brain is an engineer, so I'm also in other kind of meetings like business meetings or engineering meetings or systems meetings. And in that kind of meeting, that kind of thing doesn't happen. People. Well, not always, but most of the time people understand each other, and even if they have very different backgrounds, they kind of are able to engage in a conversation and communicate and add value to the meeting. So what is it that makes data science so difficult to be able to engage in a conversation with people from very different backgrounds? And that actually entails with education. So how are we going to educate people? So that kind of situations happen less and less because people understand what they are talking. And so if we think about a situation where we put a physician and any other person, and they try to predict from the picture of a footballer if he's going to overtake or not, people actually, they will be able to engage in a conversation trying to discern if the guy is going to actually kick it or not. And why is that the case that they understand each other? Of course, the physicists, which will be the equivalent of data scientists, who know much more about the field, will be able to, with precision, define what is going to happen, and the other person not. But they still are able to engage in a conversation. So why is that? Well, I think that's because there is a common body of knowledge that we are all trained on that has been chosen at some point in time. We got that given in our education, which involves several basic models about physics. So even if I don't know the details, I know that force is equal to the mass and acceleration. And from that, and having a look to how the guy is going to kick, I may be able to at least discuss with you if the guy is going to be able to succeed or not. But that also happens in business. I mean, even if you are not a person who knows the nitty-gritty of microeconomics, you know the offer and demand law, and so we can have a chart if the new change we are going to introduce is going to affect the demand in a good or a bad way. And in a more general sense, I mean, we have the laws. We more or less have a common knowledge of the laws, even if we are not lawyers, so you can have an idea if you are one step closer to jail or not. So I think this is what is missing in the education on machine learning and data science. And if people still not engage in conversation, that means we are doing something wrong. Or probably we have chosen the wrong kind of knowledge to teach the people. So when you see courses all around in the internet, in Coursera and all these places, they are great, but sometimes they are missing the fundamentals. And data science and machine learning has some fundamental results that are not specific to any kind of algorithm. They actually are the foundations of the principles we're following to build algorithms. So let's, very quickly, because I've been told we don't have much time, to try to give you, I have chosen just 3 results from learning theory. So first of all, what is learning theory? So learning theory has started a long time ago, before data science was so pervasive. And in that kind of area, what they try to specify is if the principles of machine learning actually made sense, and to what extent we can have some kind of guarantees on machine learning. And I have chosen just 3 results, which I think everybody should know. And if everybody would know them, it will help a lot on engaging in conversations, even if you have different backgrounds. So first of all, the first thing everybody should be aware of is how the mind of a data scientist, a person that has been trained on, think like. So when you're expressing a problem or expressing your idea of a product of data science, the first thing the data science is going to think about is, okay, how I'm going to put this in numbers, how I'm going to translate this into numbers, and that is the domain. And the next thing he's going to ask you is, where is the data set? Where do you have the data set that I'm going to put into numbers? So from that point, he will jump and try to think about an hypothesis space. What is a hypothesis space? It's just a set of functions where he's going to choose the final model from. So when we say, I'm going to use a neural network, you are committing from that point on that your hypothesis space is going to be all the possible neural networks that you can achieve from a data set. And once you commit to that, you actually feed the data set to an algorithm, a training algorithm, a piece of code that actually is going to combine and is going to select from your hypothesis, all the possible hypotheses you have, the correct one, and you're going to evaluate with a loss function. Just from that, we can see that some people in the previous slide were wrong. So when you tell me, here you have the data, but why do you need to know about the data? Well, I need to know about the data because I have to select my hypothesis space. If you tell me that if you put me in a position where I don't know anything from where that data comes from, I will be basically tossing a coin here, and I will just select one just out of nowhere. And also, the person who will say, okay, just tell me if it makes sense or not, but I'm not going to give you a reference where you can evaluate from. So if you tell me that, how I'm going to give a feedback to a training algorithm to know which of the functions is actually the right one from all possibilities. And from this point, you go to the first result. We're going down to a little bit technical here, but I will just give you 1 second and try to remember the colors about anything, because they will be used in the next slides. So no freelance theorem. So you can find this in a lot of books, but what you cannot find is actually the mathematical expression of it. So the no-freelance theorem, it was proven, I don't remember, a long time ago, like probably the 80s or 70s. And it says that for any algorithm, any learning algorithm that you can think about, and any domain, which most of the time is infinite, and for any data set that is smaller than half of your domain, think about if your domain is infinite, half of the infinite is going to be a big set, even if you have a Hadoop cluster. There is a high probability, not high probability, but there is a reasonable probability that even if there is a function that will actually solve the problem perfectly, you will not find it. And you will have an error bigger than a constant, which is around 20%. What is this thing telling us? Well, this thing is telling us many things that we will see in the next slide from the business perspective. It's a mathematical result, but it actually tells us a lot about business. But first, before that, it seems, let me complete it, because it seems very not optimistic in some sense. So if we are guaranteed that we're there is a probability of failure, then what is this data science about? Okay, what this theorem is saying is that for any learning algorithm, there's going to be a problem that you can find that the algorithm is going to fail on. But what it's not telling you is that you can find another algorithm that is going to succeed in that very same problem. So what data science is about is actually trying to find different algorithms for the perfect kind of problem. So what this basically exploded is that, okay, nowadays it seems, Paco Nathan was talking about the tribes in the morning, and so this no-freelance theorem actually make all these tribes appear. And from the point on that we know that we are not going to ever have the perfect algorithm that solves any problem, we have to come up with different kind of algorithms and hope that for a new problem, one of those is going to fit in. But let's read this from the business perspective. So what this tells me, if I'm a manager or a human resource or a person involved in recruitment for a company that wants to do data science, well, if you will always have the possibility that you will need to find a new algorithm for a new problem, you have to be prepared and you have to invest in a variety of specialists. And a second thing that you should escape from is from anyone that tells you that there is this killer technique that is a hammer and will solve all problems. Because you have a mathematical certificate that that's not possible. It's impossible. It will never happen. You will always be in a possibility of finding a problem you cannot solve with that hammer, and you will need a new technique. But it also tells things to data science teams. For data science teams, what this thing is telling us is that even if you have learned all possible algorithms, and you have, no matter how many problems you have seen, you will always be in a possibility that you will find someone that you will need to apply a new technique you never saw before. Or you may need to come up with a new technique that it didn't exist before, because all the ones that we have don't fit your problem. So that's actually something impossible for just one person to do. So all these advices that you get for data science teams in big companies or in medium companies, where they advise to do workshops and to share experiences from one team to the other team and do lunch breaks and all this stuff. What this is actually helping is reducing the probability that for a project to fail, because you will learn the more experience you learn from, the more you're going to reduce that probability, because your toolbox will be bigger. Second kind of result you can find in learning theory are generalization bounds. And this comes to giving an answer to the last person in the first slide, or in the second slide, who was saying, what, you have to be wrong. I mean, there is no, do you have any guarantee, do you have any certificate that your algorithm actually found something sensible? So what generalization bounds tell us is, answers to us is, how can be sure that a model will not fail in production? What is the process that we should follow? And how we can correct things when they are not going well. So when a data science project gets stuck, how can we react? Which knobs do we move to try to move it in a proper direction? And more from the big data perspective is how can I know if I'm being wasteful in my data science approach in terms of data and waste of money, saving all the data and storing all the data, managing all the data. So generalization bounds have some shape like that. So the blue part here is with high probability. So you can think this as like close to 99%. The error that we're going to get in production will be when you do a data science process is going to be less than the errors you observe in your training set where you're building the model plus an extra bound that depends on two main components. One of it is the amount of data you have used to train the model, and the other one is the complexity of the hypothesis space you have used. So out of this, the most difficult part of picking probably is the complexity. So you can think of complexity and as how rich is your hypothesis space. So every time you add a layer to a neural network, you are increasing the hypothesis space. You are making it more complex because it can handle a bigger set of functions. Every time you go from a linear classifier to anything that is non-linear classifier, you are increasing the complexity because non-linear are more general than linear. So think of it like that. So how can we read this rule of thumb in practice? So I have just gathered this list of advices on how to manage a data science project in a general perspective. And I will just, on purpose, I just put this rule of thumb on the left. So when they tell you, well, if it doesn't work, get a larger sample, what they're actually telling you is that, well, it may be that when you apply this on your test set, that your generalization is going bad because this bound is actually not very good. So if you increase this number of data points, you may be able to make it work better in production. When they tell you change the model you're using, change the algorithm, what you're actually changing is both quantities. You are maybe using an algorithm that is going to model better in training, and also maybe the complexity of it is a little bit more mild, and you have put the right bias to the problem you're doing, so then the generalization works well. And so on and so on. So if you start reading this rule of thumb, or think about it when you're thinking about the project, that very project that is not going well, you may also probably find a route to give an advice or engage in a conversation about how we're going to go about it. But it also has a reading from the big data perspective that I haven't seen very often, and I think is something that we should reflect on. When you see the algorithms that are available in Spark and in these libraries, actually, we're kind of in a limitation of what can we implement in a MapReduce framework. So the models that usually appear there are a little bit limited from the point of view of complexity. So the complexity of the hypothesis space they manage is not very high. So on the one hand, we are saving huge amounts of data, and on the other hand, we are applying very low complex models. So the question is, do I need to maintain all this data? So I usually see the case where there is a huge amount of data, but we are doing linear regression with maybe 5 dimensions. So you don't need to go to petabytes for solving that kind of problem. If you're actually going that way, you're actually wasting money invested in all that data. And the theory actually tells you that. So you could read it from the theory. It's not me telling you, it's the theory telling that's wasteful. So many times I find this, I call it the half-pie syndrome, where on the one side there is a huge preparation and a huge investment from the business side on putting all the data together and making sense of it and building a data lake and making it available. But on the other side, the data science is not very planned because maybe it's not that much understood. So you're actually, it's like when you need a sugar rush and you buy a pie, but when you go home, you actually only eat half of it and you realize, you have been wasteful. So we're building data lakes, and from the statistical point of view, many times in many places they are only eating even maybe a quarter of it, and the rest statistically is wasteful. So one reading of it will be, okay, just slow down in getting all that data, or maybe the wiser advice is you can always Andrew Gellman put in a quote sometime that there is never an amount of data that is large enough. If you have reached that point where you have solved the problem, you have good accuracy, it's working well in production, but probably you don't need that much data to achieve that. What you should do is start planning what is the next problem, the next more challenging problem that you're going to tackle. So you have to use a more complex model, and then your data is giving you the value at that point. One latest, a bit even modern view on big data bounds that I want to finish with is that, so these bounds were actually proven a long time ago, and they were thought through when the data was scarce. We were not gathering that much data, so they wanted to be the most effective as possible with the data they had. But now we are actually in an opposite situation where we have more data that we can actually use. So if the amount of data and this generalization bound is not the problem, then what is the problem? Okay, so from a theory perspective, you can also divide, and there's a paper from Chappell which is very interesting, that they divide the error in production that you get in the approximation error, which is the error that there is a limitation. I mean, sometimes you cannot go lower than some limit, plus the estimation error, which is the error in the generalization bound, that depends on the complexity, the combination of complexity and amount of data you're putting in. And also it depends on the optimization. So that algorithm that tries to find the optimal function from the hypothesis space, it maybe it's not doing as good as it could, and it's getting stuck in a local minima, or it's getting stuck before it converges, or something like that. And that actually brings me to the last concept I want to put, that you not only need a variety of people to be able to find the right bias, because there is no hammer, you also need good engineering to make something made a project successful. I've seen sometimes that people think an algorithm is not working just because it is too slow to converge, or maybe the optimization algorithm chosen is not the right one, or they have done something wrong in this red area. So never forget to not only have the mathematician, not only have the creative person, but also have good engineer behind them, backing them. Because many open source libraries that data scientists use are not optimized, are not optimal out of the box. They have some limitations because they are done maybe in academic paper, and then they are just sometimes taken to production. So make sure you always have some engineering team that actually solves that limitation. So that brings me to the end of the talk. Just 3 takes from it. Probably, from my point of view, I think education should go more on teaching the fundamentals of machine learning more than specific cases or specific algorithms. And we should aim in the education, in the global education about machine learning, on having sound rules that allow us to engage in a conversation between any stakeholder in a project. And I think learning theory bounds are actually a good modeling of machine learning that can actually help us to achieve that. Some references where you can find all these results that will be published with the slides.